Yeah, as I said, it's a great pleasure being here in KubeCon, and thank you all for coming. We have a bit of a long title for our talk, but basically we're going to talk about optimizing swap. I'm Itamar from Red Hat. My friend here is Ajay from Google, and I had the privilege to lead swap development until graduation, which is something that I'm super excited about. But let me tell you, this was not easy at all. When I started looking at swap, it was in the 126 era. And back then, swap was only supported in an alpha and was very experimental in initial implementation. And the developer that started it soon after left the project. So there was no real development or any interest around it. I had to gain interest around it, prioritize it, and basically convince people this is important. But even then, people are rightfully very cautious about this because it's such a fundamental change in Kubernetes. So as you can see, it has been many releases and many beta versions, but I'm very excited that it finally had reached full graduation. And one of the things that allowed it to graduate eventually is that we have framed it as a basic swap enablement feature. So we understand that there's more work to be done in order for the feature to be complete. And we are already working on 3 follow-up enhancements. This is a great time to collaborate. So if you want to, you're welcome. Basically, we're working about pod-level swap controls and making evictions and scheduling swap aware. So that's basically the plans for the future. So one of the problems or challenges with swap is that it requires a lot of configuration and tuning. And this is something that kubelet cannot do for you because kubelet runs in a very limited scope. So it's a system daemon. It cannot edit OS configuration and certainly not hardware. That's out of scope for kubelet, but that's fine because that's when you as an admin can come into the picture and do a lot to optimize swap for your use case, which is actually a real necessity with swap. So generally speaking, when you'd want to use swap, you'd have to go through 3 phases. Deploying it, configuring it, and eventually you'd probably want to monitor it and make sure everything runs as expected. So let's talk about the hardware you'd use. So when I started dealing with swap, I basically treated swap as a safety net for disaster situations. And in this kind of use case, you'd probably want fast hardware like SSD and VME. But what I found out is that basically the use cases, the range of use cases around swap is huge. So people use it in very different ways. So for example, some people use workloads that simply allocate garbage memory that would never be accessed by anyone. So this is a very different use case. For this use case, you might want to choose more affordable hardware like hard drives. Another use case is applications, legacy applications that just expect swap to be there. They won't even use it in any way, but they just want it to appear there. And for this, you can use something like over-the-LAN devices. The key point here is that it surprised me how wide the range of use cases around swap is. Another thing is that swap can be generally deployed in 2 ways, either in a swap partition or with a swap file. So now a question to the audience, like which one of them do you think is generally better? If you think that partitions are better, raise your hand. Okay, if you think that files are better, raise your hand. Okay, more or less 50-50, right? So in my opinion, file is the winner, and let me tell you why. So first of all, there is a misconception around file swaps is that they are slower than partitions. This used to be true a while ago, but it's not true for a long while. So this fact is not very well documented anywhere, which is pretty surprising. But there are some proofs here. So Chris Quote, which is a memory management kernel developer, another one from the Linux dev mailing list, and Baildang blog posts. But yeah, this is not very well documented. But swap files are not slower than partitions. They even tend to be a bit faster. But that's not a great advantage of using swap files because swap files are highly flexible. You can easily create them, remove them, resize them. This is generally the best choice. Another question is, should we deploy swap on control plane nodes? So obviously, control plane nodes are crucial, and degrading performance could have dramatic effects. So this is generally not recommended. So think about processes like etcd, which keep most of their stuff in memory. Swapping it out would be dangerous. One possible exception for it is single node clusters. This could theoretically be a use case, but to be honest, I haven't tried it, so do it at your own caution. Another thing is that it's generally recommended to use a dedicated disk for swap. So swapping can use a lot of I/O, and this kind of situation can starve basically the main disk with respect to I/O. So using a dedicated disk is great for separating the I/O pressure between the main system and the swap device. Moving to the configuration part, so and still in the I/O topic. So there's a cgroup knob that you can use. It's called I/O latency, and with that you can give I/O priority or to the system slice, which means that basically whenever a system level process would want to use I/O while workloads are trying to swap, it will always get precedence. Which is a very recommended thing to do, especially if you're not using a dedicated disk for swap. Another question is, should you allow system daemons to use swap? So this is very use case dependent. It makes total sense that some of your system level daemons would be great candidate for swaps. I'd generally recommend to disable swap for the system slice at the beginning and then allowing it on a per application or per cgroup basis, which is something you can do. So with cgroup, there is a memory swap max field, and this way you can control it on a per cgroup granularity. Another question is, should you let kubelet itself to swap? Again, sorry, I'd start with not doing that, but I can think of theoretical use cases on which this might be a good idea. So another trick for opting out swap at the container level is that if you set memory limits that are equal to memory requests, this container would opt out of swap, which is very useful for some use cases. So for example, if you have an idle process that the kernel would think is a good candidate for swapping, but that needs to be very responsive, you might want to consider opting out of swap for this container. So this way you can do it pretty easily, and it's yeah, it's a trick to achieve that. So moving to the last thing that I want to talk about is monitoring. So monitoring with swap is very confusing. One of the most confusing metrics is swap usage. Swap usage tells you almost nothing about how pressured the node is, because of two reasons mainly. So first of all, workloads won't use swap only whenever there's memory pressure. So if a single container reaches its limits, the kernel will try everything in order to avoid killing it, which includes swaps. So the kernel could be busy paging out, moving pages to swap, even if there is no general pressure on the node. Another thing is that the kernel works very lazily with swap. So even if some process allocated has like a lot of swap space and the process dies, it will not get updated right away. So if you use something like free to check the swap usage, it would tell you that there's a lot of swap usage, but the memory there is just irrelevant. So this is a very confusing metric. A better metric is the rate of swapping pages in and out. So if the kernel is constantly busy with moving pages in and out of swap, That's a better metric for, or better indication for the system being under pressure. The biggest problem about that metric is that it's not normalized at all. So how many pages do you need to move in a millisecond in order for it to be considered as pressure? But this is a better metric. Another great tool for that is PSI. PSI is not yet fully supported in Kubernetes. It had just graduated to alpha, but we're certainly keeping an eye on that for swap. We also added kubectl support. So now when you do kubectl top node or top pod, you have the -- show swap flag option, which can basically tell you which nodes have swap, don't have swap, what's the capacity, what's the usage of every pod, which also can be very useful. And also, now every node advertises the swap capacity that it has. This is also very useful for two reasons. So obviously, to know that swap capacity on a node, but also if swap is not deployed on that node, sorry, this field will be omitted. So this can also be useful for scheduling purposes or things like that, and to understand which nodes actually have swap deployed on. So thank you, and I'll let Ajay take it away from here.
All right, thanks so much, Itamar. My name is Ajay. I'm a software engineer at Google. I spent some time stress testing SWAP on Kubernetes, and my goal was to to understand whether it brings stability or just move the problem around. It wasn't just to see whether SWAP worked, but when it breaks, how it breaks. I think that's what we want to take away. Okay, first I want to discuss our experiment setup. This was done in GKE. And we used a memory burner pod to simulate different load patterns like spikes and gradually leaking memory, and how SWAP is able to attune to that. So it's a burstable QoS with high limits and high requests. And high limits are to ensure that the pod swap utilization isn't limited by the C group limits. And high requests because in Kubernetes, SWAP is modeled such that higher memory containers get higher pod quota. So that's the reason why we maintain the experiment setup like that, to ensure that we are able to push the boundaries of swap utilization on the pod. So our finding was that kernel tuning is not optional, but it is essential for node stability. We look into the problems and the results from two main axes. First is kernel parameters on what we should tune, and the underlying hardware I/O profile for different results. First is a visualization. So this is plotted from VM stat metrics on the node when our experiments were run. So this graph shows usage metric from one of our experiments. What you're seeing here is a 8 GB GKE node, and SWAP was on the default persistent disk, PD balanced. So it's a SSD network attached disk. And this is when we tried to capture a memory burst of 200 megabytes per second. Here it shows the workload also has 2 gigabytes cache over here as part of the workload. And this is an experiment setup. As I talked about, each experiment was done with 3 reruns, so that the bursty pod is rerun 3 times to avoid any random or fluke errors as part of our experimentation. And I want to point out a few things here, particularly if you see this is a SWAP activity. If you see the spiky actions here, this shows that SWAP activity is actually happening in cycles. It's not like a one-shot get out. And SWAP activity is also highly paralleled with the I/O activity, and there is also increased CPU usage corresponding to the SWAP time. So how do we read that? So you could note the high I/O wait times. So these are the CPU time shares. So the green ones are the I/O wait times. So basically, it's I/O bound. It's a percentage of CPU time that it's waiting on SWAP I/O to complete. While we are at here, I could also give you some details about kswapd, which is the kernel daemon that's responsible for swapping in Linux kernel. It is a single-threaded single-threaded entity. So even in a multi-core system, it doesn't gonna be like increase the swap performance. So what does it mean? Like if your K-swap is like even very active, it's gonna be 100% CPU because it's just gonna be sitting on a single core. And however, on a NUMA nodes, K-swap daemon will spawn worker threads for each of the NUMA node. So each zone will be like managed swap with its own thread. So if you see multiple threads, it's because like it's your NUMA architecture. And they act independently on the memory zones. So each independent zone limits determine the swap triggers for the zone. And as I discussed, swap is like largely a IO bound activity. So using a backend storage that is fast enough to keep the IO latencies less for your load is so important. From my experiments, there's a huge performance difference and also the stability risk between a hard disk drive backed swap device and the NVMe backed swap device. So yeah, that's what else to see here. What more is that swap as a resource is released lazily. So if a pod that is utilizing swap is killed, and you see that like, okay, swap is not yet released, it's because like swap cache can be lingering around for some more time, but it will be freed up as soon as it ages out or when there is another process or another pod that really needs it. So that's some background on K-swapd. Let's now talk more into tuning. So what is like our first test was on swappiness. Now this is a well-known parameter on swap, vm.swappiness. So it tells the kernel what to prefer during the time of reclaim, like whether it should drop the file caches or whether it should swap your anonymous memory off to the disk. And anonymous memories are basically your program heap and stack that has all your allocations. So that's the only candidate for swap. And kernel considers swap as expensive by default, so it slightly prefers dropping like clean caches because it's also quicker for it. You can modify this behavior with this setting. You can make it tune it such a way that like you could keep your cache longer than the swap. Okay, and let's break some myths about this parameter. Does setting swappiness to 0 really protect your workload, like prevent your workload from swapping? No, it's really not. If the memory pressure could not be contained by the kernel by just like dropping the caches, then the kernel would tap into the swap, like if it is available, like as long as the C group controller allows it. If you really intend to like restrict certain workloads to not swap for performance reasons, I think that you should prefer to run them in guaranteed QoS in Kubernetes, and better you can isolate them like on a non-swap enabled node. And another one is that does higher swappiness setting like mean more data will be swapped? Not really. It depends on the memory pressure on the node. If it cannot be contained just by dropping the cache, reclaim will pick swap up to the limits that you configured for. And another thing I can add here is that when you configure multiple swap device, does it fill up one and go to the next? Like people will think like, oh, I can configure hierarchy of swap devices like in the order. It's not based on the order. It will go on a round fashion. But you can set priorities to make sure that like your higher or like your expensive swap, low latency swap is utilized first before tapping onto the something slower. Okay, and there's one more graph. So this graph compares a lower swappiness setting and a higher swappiness setting. If you look at the right, the swap is more eagerly utilized compared to the left. If you look at the cache utilization. Swap is an entity that brings down the memory pressure. What I graphed at the bottom is a PSI pressure matrix. So as I said, like swap brings down the memory pressure. So when swap is not helping your pod, it will be evident from memory pressure building up over here. Like here you see this because like this pod was configured with 26 gigabytes of limits, and the container is like losing the utilization, so it's panicking. The pressure basically is reflecting on the memory pressure because like even though swap is there, it's not able to utilize, and it is hitting the C group limits. And another thing is that you don't see any CPU pressure here. The reason being that This was a multi-core VM, and even when swap is very active, it's not like utilizing across. So likely that that this C group tasks are landed on a different core and it is not affected. And most importantly, what you see here are the I/O pressure. So when swap was actively trying to push as many pages out to the disk, you can see the I/O pressure building up on the C group because it's not able to be have more control on the I/O. Yeah, I think we can go on to the next. Excuse me. Okay, if swappiness is what to swap, watermarks are when. So this determines when memory reclaim actually starts for a node. So this basically is like some theory over here. So memory reclaim, think of it like a game of race. Your process wants to allocate more and more memory, and the kernel wants to move them, like the inactive pages, back to the disk. For things to run smoothly, we want to give more time for the swap daemon. So it is essential for us for a node to be swapping early and gradually, so that swap wins the race and we never hit the minimum watermark. So minimum watermark is when app freezes happen. Basically, kernel tries to synchronously reclaim the pages. It's not the background kswap daemon thread anymore that is pushing pages back, but it's actually your process thread that's trying to move the pages. So how do we control it? How do we start early and gradually? So there are two kernel parameters that you can adjust to set an early preference for swap. First one is min free kilobytes, and another one is watermark scale factor. There are others, but these two are the important ones. So here it shows how by updating these parameters lift my watermark levels up in my Linux node. This is a non-NUMA node. So I have a zone info where the normal zone is capturing the pages that's reflecting the water levels. This is how you can observe where my swapping would start. So if your instance is in NUMA architecture, you will see many of these zones, and each zone, as we talked about, have its own swap octet. And in this case, by setting min free kilobytes as 500 megabytes and watermark scale factor 1000, I was able to adjust swap start at when 3 gigabytes of free memory is left on the node. Okay, and how does it actually look like? So this parameter adjusts the free memory reserve for the kernel, which is the min watermark level, the blue zone over here. This also relatively scale the other reclaim levels as well. So it helps to lift the critical points when kernel handles emergency actions. By default, in my node, the buffer is 67 MB, which puts the start of swapping to be 88 MB, which is actually really low for many of my testing. You really couldn't see any swap action. By adjusting the kernel reserve up, you give more time for actually the killer action, because if killer couldn't bring down the memory pressure, then where the kernel will be panicking. So this is important to lift this boundary up. And this is VM min free kilobytes in action. So if you see the left, I have a 500 megabytes, 500 megabytes of kernel buffer, set to the min 3 kilobytes, and on the right, it is 1 gigabyte. I'm trying to load up, observe a load of 500 MB per second of rate. It's a local SSD backed swap. So just by pulling up the minimum watermark level, I'm able to kickstart swap earlier. And even though the previous one had swap activity, it was not able to sustain the rate of growth. Here, if you compare with more time for swap activity, node was able to protect the workload from actually kill. And see this rate. So previous, I think what I showed was a persistent disk that's network attached. Even though it's an SSD, it was able to capture about 150 so swap rate, but here it is, the nominal rate is around 300, 350. Again, this changes from, like, you could do your testing to see what sits on your disk, because in a cloud provider setup, it may be a network attached, so you would see different rate. And this shows the swap utilization picking up, and this is when free memory is falling down because swap offloaded it. Okay, and next one, the other parameter is I want to talk about is like watermark scale factor. Now this changes the low and high watermarks alone, whereas the previous one, what we talked about, lifted everything because it's lifting up the min watermark level. Now this time we keep 500 MB as the min free kilobytes, but I have scaled the scale factor to be like 1000 and 2000. You can see how the swap, like start threshold has moved up significantly. Basically, we are giving more room for swap to act, and the default is 10, as we shown here, and you can set a maximum of 3000 that would start a very early swap activity. Now this graph shows again how adjusting the scale factor I can protect my workload. So by proactively swapping, I was able to help my workload avoid a home kill scenario. It's starting to swap around 30 seconds, where in the case of here it is 50 seconds, and that swap wasn't enough to absorb my 500 MB load. Yeah, okay. Okay, now we talked two things. I just wanted to re-emphasize the parameters on what they do. Now, the raising the min watermark creates a larger safety buffer for the kernel. Now, with scale factor, you widen the runway for swap to act gradually. So, by defining the amount of memory left in a node before, K-swap daemon is woken up, and by when it stops freeing up memory, you are basically controlling the aggressiveness of your swap activity on the node. And the trade-off is that early swapping has early reclaim, so you have better control on the memory, and versus you're spending CPU cycles for your swap activity. And in my preference, early and gradual swapping is better than late and aggressive freezing, because as we talked about, when do you see application freezes? Not in my case, not during the swapping activity, but actually when the min watermark was hit. That's because kernel is trying to do synchronous reclaim. Okay. And I also want to share two problems with eviction as we are talking about reclaim. First, with proper kernel tuning and faster storage setup like NVMe backed swap locally attached, system can be configured to gracefully swap and evict workloads, often without triggering home kill. However, if there is rapid memory pressure, Kubernetes cannot really help, because home killer is faster than Kubernetes eviction. Kubelet has to keep polling cAdvisor to see whether memory is available on the kube system's C group space. That is slower than home killer's triggers. So home killer might still be invoked before kubelet can act. So it is recommended to tune your thresholds, lift your kubelet eviction threshold, and allocate some system reserved memory to ensure that you have some buffer for Kubernetes to act on it, because Kubernetes eviction is better for you because the workload can move to a different node, or it can give graceful failures. You don't want your workload to be abruptly terminated. And second, kubelet eviction, this is another eviction blind spot. Kubernetes eviction currently does not account for swap usage. Say you have a workload that has 10 gigabytes of memory offloaded to swap. Now, the Kubernetes will not see the swap usage. To it, the memory usage is basically what's on the RAM, physical RAM. It is only considered for eviction. Yeah. So this is another. I just wanted to show the iterative process. This graph shows how you can do step-by-step experiments to have a better outcome. With applying all the settings we talked about, with no tuning, I have no swap utilization with 128 MB of kernel buffer. With just adjusting my tuning, I'm able to increase the swap utilization, and eventually with 500 MB of kernel buffer, I'm able to protect my workload from being evicted. So that's the sweet spot we want. So this, in summary, these are the key kernel parameters I want you to take away from the talk today, how you could control swap. And this is from our experience, our early swap configuration. So these can be a good starting parameters for tuning, but again, this is application dependent, so definitely recommend to perform your own tuning with your workloads to decide the best outcome. And I would prefer SSDs and separating, as Itamar said, like separating swap IO from your application or kube system traffic, because you don't want IO interference or noisy workloads because of swap. And yeah, I think I'll open for questions. Thank you. So the question was on GKE, so whether the swap activity and IO activity is visible. So swap activity, what I have there was on the node, but we capture, in Kubernetes, we capture like swap usage at pod level, like, container level and node level. So swap utilization you can actually observe, it's available. And IO activity, I think there are already existing metrics on IO activity which you can tune and you can capture, yeah. Oh yeah, so the swap is available from 1.34, and I think the kubectl support was added in 1.34 as well. It should be available on, 1.34, yes.
Yeah, thank you. We'll be right here for more questions.
Yes.
Thank you very much.
Thank you, thank you.